Today, we're going to go through the mathematical derivation of Lagrange points. A Lagrange point is an equilibrium solution to the differential equations of motion of the circular restricted three-body problem. This part is fairly standard mathematical language, equilibrium solution to differential equation. This part has to do with orbital mechanics, and we'll get back to it in a minute. A Lagrange point, but in other words, is any point in a two-body system, such as the Earth-Moon system, where a satellite could be placed, a satellite of negligible mass could be placed, and essentially be left there forever without any additional fuel cost. There are 5 such points in any two-body system. There are 3 that are on the line connecting the two bodies. L3, which is about the same distance from the Earth as the Moon, but on the other side of the Earth. L1, which is between the Earth and the Moon, and L2, which is on the far side of the Moon. There are 2 more points that form an equilateral triangle with the Earth and the Moon, L4 and L5. We're going to call the distance between the Earth and the Moon L. So each side of this triangle is of length L. So even though we know where the Lagrange points are, and we have data about them which we'll use to verify our derivation, we're going to go through the math as if we don't know what the answer is, the way Euler or Lagrange might have when they were first discovering these. According to Wikipedia, L for the Earth-Moon, 384,400 kilometers. So L1, 326,390 kilometers as measured from Earth. L2, 448,900 kilometers, and L3, negative 381,680 kilometers. This would be a good time to mention the coordinate system we're going to use. The x-axis is going to point in the direction from Earth to the Moon, and it's going to start at the barycenter, or the center of mass between the Earth and the Moon. But I'll get into more detail on that in just a second. The y-axis is going to be pointed this way, perpendicular to the x-axis, and in the direction of motion of the orbit of the Moon. So in this drawing, the Moon is orbiting the Earth in this direction. Wikipedia doesn't list specific values for L4 and L5, so we're going to have to do a little bit of trigonometry for those. Since we know this is an equilateral triangle, we know that each angle is 60 degrees. And we can bisect the triangle into 2 right triangles. So now this angle is 30 degrees. So the sine of 30 degrees is equal to the opposite of the hypotenuse, and the opposite is our x-coordinate. Sine 30 is equal to x divided by L. Well, we know that sine of 30 is equal to 1 over 2. So we know that the x-coordinate for L4 and L5 is equal to L over 2. Likewise, we can say that the cosine of 30 is equal to the y-coordinate divided by L. And we know that the cosine of 30 is equal to the square root of 3 over 2. So we can say that the y-coordinate is going to be the square root of 3 over 2 times L. And since we have L4 and L5, their x-coordinate will be the same, but the y-coordinate is going to be plus or minus. So first, let's set up a coordinate system. We're going to start with an inertial coordinate system that we're going to call x0, y0, y0, and z0. The origin of this coordinate system is going to be at the barycenter, or the center of mass, of the two bodies. We're going to call Earth M1 and place it here at some distance x1 away from the origin. And then we're going to put the Moon over here and call it M2 and put it at some distance x2 away from the origin. Now we're going to set up our rotating coordinate system where the x-axis is fixed in the line that connects the Earth and the Moon. The y-axis is in this direction, the direction of the orbit of the Moon around the Earth. And the z-axis is the same as the z-axis in the inertial direction. So I mentioned that the origin of this coordinate system is the barycenter, of the two masses, or the center of mass. So let's recall that the center of mass is equal to the sum of the masses times their position vectors over the total sum of the masses. And one quick note, I'm going to use a little hat above a value to indicate a unit vector, and a small arrow looking thing to indicate just a regular vector. So if we get back to this, if we write this in the rotating coordinate frame, we're going to see that we have negative m1 x1 plus m2 x2 is equal to 0. Why is it equal to 0? Well, because we said it is. Because we said that that's going to be the origin. I'm also going to note that x1 plus x2 is equal to L, what we defined as the distance between the Earth and the Moon. So we can do a little algebra now, and we can write x1 and x2 purely in terms of m and L. So we'll use these a little bit later. A couple more items of setup that we got to do. So one thing is that we want to be able to write the rotating coordinate system in terms of the inertial system. For that, we're going to define this angle theta, which is the angle between the inertial and the rotating system. So then, using that angle, I can say that I can write x as the cosine of theta times x naught plus the sine of theta times y naught. Similarly, I can write y, because if you note, this angle here is also going to be theta. That's going to be equal to minus sine theta x naught plus cos theta y naught. And then z is simply going to be z naught. So what else? We're going to say that there's a spacecraft here somewhere, and we're going to call it M3, and it's going to be at a position XS, YS, ZS, where S is for spacecraft, and that's going to be expressed in the rotating coordinate system. Let's see, let's throw in a couple of assumptions. So this is where we talk about what I mentioned earlier with the circular restricted three-body problem. So in the circular problem, we assume that M1 and M2 are orbiting each other in a perfectly circular orbit, or rather orbiting their barycenter in a perfectly circular orbit. We are going to use that assumption, but not just yet. First, we're going to assume that they're in an elliptical orbit about each other, so that we do the math for the equations of motion in the elliptical case. Then we're going to add in the assumption of circular orbits and eliminate a few of the terms from the equations of motion. So to start with, we're going to say bodies in an elliptical orbit. Then there's the question of the R term, restricted. What does that mean? Restricted means that the mass of the spacecraft is much, much smaller than the mass of either of the two primaries. This means that the gravitational pull of the spacecraft on the Earth or the Moon is so small that we can ignore it. But of course, the gravitational pull of the Moon on the spacecraft, of the Earth on the spacecraft, and the Moon on the spacecraft is something we're going to consider. So for that, we're just going to write M3 is much, much less than M2, and we're also just going to note that we're assuming that M2 is smaller than M1. This isn't really necessary, but it's how we're defining the problem. One more thing I'd like to note is that many academic papers and other resources that talk about orbital mechanics will assume that certain quantities here are equal to 1. For example, they'll say that x1 plus x2 is equal to 1, and that m1 plus m2 is equal to 1. I'm not going to do that, because I think it makes it a little bit clearer when you leave all these things in here. But just know that you might see that if you look for this information elsewhere. Okay, now that we've got our coordinate system set up, we can move on to finding the equations of motion. Okay, now it's time to derive the equations of motion for the spacecraft. To do so, we're going to use F equals ma. So we're going to come up with an equation for the acceleration of the spacecraft and then we're going to sum the forces acting on the spacecraft, set them equal to each other, and this is going to give us some equations of motion. So to start with the acceleration. So I'm going to note the position vector of the spacecraft as r, and as we said in the previous page, the position is x sub s times x hat plus y sub s times y hat plus z sub s times z hat. Briefly, I want to explain why we look at this in the rotating frame as opposed to the inertial frame. Well, we're looking for stationary points, right? So if we consider the inertial frame, if you have an object here and in the inertial frame and it's stationary, the Earth and the Moon, they're going to keep rotating about their center of mass, and the forces on this spacecraft are going to keep changing. And so you just think about it sort of intuitively, and it's like it doesn't make any sense that some fixed point in the inertial coordinate system is going to actually be able to remain stationary. At best, you could put something at the very center. You might think that, you know, it's the center of mass, but the forces are very unequal at the very center. And so actually, the very center actually happens to be inside the radius of the Earth. So that makes it kind of a moot point. But even if it wasn't, it would definitely be closer to one than the other, and it's not going to be. So we have the position, and so we need to take the derivative twice in order to get the acceleration vector. There's a shortcut for doing this, and it's known alternatively as the basic kinematic equation, transport theorem, or simply time derivatives in a rotating frame. That's how you'll find it on Wikipedia. So in the interest of not introducing any new concepts, or trying to use as few concepts as possible to do this derivation, I'm not going to use this shortcut. And by the way, these aren't three different shortcuts, they're three different names for the same thing. You can feel free to look this up on Wikipedia and get comfortable with it on your own time. But to take this derivative, I'm just going to use the product rule. So let's consider the velocity. That's equal to r vector dot. So by the product rule, we're going to have xs dot times x hat plus xs by x hat dot plus ys dot times y hat plus ys times y hat dot plus zs dot times z hat plus zs times z hat dot. And of course I'm using dot to refer to a time derivative. Real quick though, let's take a look at z. I'm going to cheat a little bit so I don't have to write as much. But so z is equal to z naught, and this is just a constant, right? It's inertial, it's fixed. So that means that z hat dot is just going to be 0. X hat dot and y hat dot, those are dependent on theta, which is changing with time. So those will have non-zero derivatives, and we'll come back to those in a second. But for right now, we can notice that we can simplify our work in the z direction. So this one goes away. That's nice. That'll make things a little bit easier for us. So now we can find the acceleration. It's equal to v dot. So now we go through the product rule again. So we're going to get xs double dot x hat plus xs dot x hat dot plus, now we look at this term, we're going to get xs dot x hat dot. So these two are going to combine, but we'll get back to that in a second. And then xs times x hat double dot. And so the ys is going to be similar. So ys double dot y hat plus, I'm just going to go ahead and combine the y terms, to ys dot y hat dot plus ys by y hat double dot. And for the z direction, since we know that z hat is a constant, we can just take the derivative of zs rather. Okay, cool. So now we're going to go back and explore x hat dot and y hat dot. If we take the derivative of this, it's going to be pretty straightforward. We're going to get derivative of cosine is minus sine. We got to use chain rule here because we're taking a time derivative. So derivative of cosine is minus sine times the derivative of whatever the argument to cosine is. And derivative of theta is just going to be theta dot. So that's going to give us minus sine theta, theta dot, and of course x naught, like z naught and y naught, is a constant. So that just stays where it is. Likewise, derivative of sine is cosine, and again we apply the chain rule. So notice now that we can pull a theta dot out of this, and what we're going to be left with looks a lot like y hat. Well, hey, it doesn't just look like the definition for y hat, it is the definition for y hat. So we can just write this as theta dot y hat. So if we look at y hat dot now, we're going to get derivative of sine is cosine, but we keep the negative out front there, so it's going to be negative cosine theta dot x naught. And then derivative of cosine is minus sine. Well, again, we pull a theta dot out. And actually, we're going to pull a negative theta dot out. And we're going to get, this happens to be x. So we can just write negative theta dot x hat. And then, as we already noted, z hat dot, because z naught is a constant, z hat dot is 0. I'll just write it here for the sake of posterity. We do have a couple of double dots as well, so we need to take the second derivative of x hat and y hat. That's going to be pretty easy since we reduced it down to these simple equations. So if we look at that, x hat double dot is going to be equal to, again, we use the product rule, it's going to be theta double dot y hat plus theta dot by y hat dot. Well, we know that y hat dot is equal to negative theta dot x hat. So that's actually going to be theta double dot y hat minus theta dot squared x hat. Cool. And lastly, y hat double dot, that's going to be negative theta double dot x hat minus theta dot x hat dot. But again, x hat dot is theta dot y, so this is going to be negative theta double dot x hat minus theta dot squared y hat. Cool. So now we can go ahead and plug these into our equation for the acceleration, and we're going to be able to write everything in a vector in terms of the rotating coordinate system. So we have a is equal to xs double dot x hat. Now we noted that these two combined, right? So let's go ahead and combine them. It's going to be 2 xs dot times x hat dot, which we noted was theta dot y hat. Okay, and then plus xs times x hat double dot, which is theta double dot y hat minus theta dot squared x hat. So now we have plus ys double dot y hat plus 2 ys dot times y hat is negative theta dot x plus ys by y hat double dot, which is negative theta double dot x minus theta dot squared y hat. And of course, plus zs double dot z hat. We have everything written in terms of x hat, y hat, and z hat, but it's all kind of all over the place. So let's bring it all together. So let's first start with the x terms. It's going to be xs double dot, and then what's the next x hat term? It's this one. So negative theta dot squared xs, and then any more, we have a negative 2 ys dot theta dot, and then minus ys theta double dot. And that's all in the x direction. So now ys, in the y direction, we're going to have ys double dot. And let's try to keep things similar to how we've written them here. So we have, in the y hat, negative theta dot squared ys, and we have plus 2 xs dot theta dot, and lastly, plus xs theta double dot. And that's all in the y hat direction. And of course, plus zs double dot in the z direction. So we've gotten our equation for acceleration. Now we need to get the equation for the forces. What are the forces acting on our spacecraft? So we're going to note that there's a force acting in this direction. We're going to call this force 1. I'm drawing it offset just a little bit so that I have room to draw another vector here. And of course another force acting in this direction, which is force 2. So this is the force of the moon on the spacecraft, and this is the force of the Earth on the spacecraft. And we're going to note this position vector. We're going to call this R13. And this position vector we're going to call R12. Whoops, I meant R23. This force is obviously the force of gravity, so for that we just use Newton's universal law of motion. Newton's universal law of gravitation. So we know that F1 is going to be equal to negative g by m1, m3, and it's going to be over the norm of r13 squared times the unit vector in the r13 direction. Well, we can write the unit vector there as equal to the actual vector r13 divided by the norm of the vector r13. And so we can essentially write f1 as negative g m1 m3 over r1 cubed times r13 the vector. And actually, this would be a good time to state this vector. So we're going to note, by the way, that r13, it's equal to the position of the spacecraft minus the position of the Earth. So that's going to be, because the position of the Earth is, this is essentially negative x1, 0, 0, as written in the rotating coordinate frame, and this one is going to be x2, 0, 0. So r13 is basically equal to xs, ys, zs minus negative x1, 0, 0. So this is going to be xs plus x1, ys, zs. And of course, I'm just using parentheses and commas as a convenient way of writing the vector. The full form of this would be xs plus x1 by x hat plus ys, y hat plus zs, z hat. So now f2 is going to be really similar. We're going to have negative g times m2, m3 over r23 squared times r23, the unit vector, which of course we can rewrite as, and of course r23 is equal to, so now we can sum the forces, it's going to be equal to, and notice that we can pull an m3 out of this. That's going to be really useful for us. So now we can set this quantity equal to m3 times the acceleration vector, which is here. But notice that because we have an m3 pulled out, the m3 is essentially going to go away. And so now we can write is equal to this quantity right here. So we're almost done. What we need to do is we need to explicitly write out r13 and r23 in their vector components like we have the right-hand side written out, and then we can match up the two sides and we'll get our equations of motion. So if we write these out, we're going to get is equal to what we have on the right-hand side there. So that's going to be, let's combine up all of the terms on the left-hand side of the equation. So we're going to see negative g m1 by xs plus x1 over r13 cubed minus gm2 over r23 cubed by xs minus x2, and this is all in the x direction, right? All we did was just combine these terms. So then we combine the terms on for the y, and then finally, great. So now we have a vector on one side and a vector on the other side, and we end up with three equations of motion. Okay. So now we have our equations of motion, but there's one more step. We're going to go back and we're going to assume that the orbits are circular. This means that theta double dot is going to be 0, because for the orbits to be circular, they have to be rotating about each other at a constant rate, theta dot. So if theta dot is constant, theta double dot has to be 0. So finally, we can write our equations of motion as follows. So now we can start to talk about equilibrium solutions, or equilibrium points, or stationary points, as you like to call them. Now remember that such a point, such a solution, is one in which xs, ys, and zs are all constants, which means that ys dot, xs dot, and all the double dots are all going to be 0. So we're going to move on to a new page and start looking at these equilibrium points. So if we write this, but set all those various terms equal to 0, what we're going to get is... I wrote something down wrong here, didn't I? This is a ys. And then this one is just 0. So we're going to get 0 equals negative gm1 over r13 cubed cs minus gm2 over 23 cubed cs. Okay, so now we're trying to find some point xs, y, zs that satisfies all three of these equations simultaneously. Now, at first that might seem pretty daunting because we have xs, ys, and zs in all three of these equations. It may not look like it, but we've hidden it inside of r13 and r23 because remember that we've defined those. Those are written in terms of xs, x, y, and z. So how do we do this? Well, first we're going to go through the algebra. And then eventually we'll see if maybe we can use some numerical methods to find these equations. But as it turns out, the algebra is actually going to help us a lot, and it's going to simplify a lot of these. So let's start with looking at the z equation. So I'm going to group a few terms here. I'm going to say that 0 is equal to negative g by... So we just did a quick rearrangement here. Negative g is just a constant, so we don't have to worry about it. But so right off the bat, we can see that if zs is equal to 0, that satisfies this equation, right? That's going to be good. What if zs is not equal to 0? Well, because g is a constant, and this is a non-zero, this quantity would have to be 0. But that's not possible, because m1 is positive, m2 is positive, the norm, the distance of r13 and r23, that's always going to be positive. So we just have positive quantities here. So that means that for zs not to be 0 is impossible. Because non-zero zs means that this equation will never be 0. So this is great. So right off the bat, we found that any equilibrium point that we have, we still need to find xs and ys, but we know that any equilibrium point we find, zs is going to be 0. And that sort of makes sense because, you know, the moon's orbiting the Earth in a particular plane. What we basically found is that these equilibrium points are going to be in the plane of the orbit, which kind of makes sense. So let's take a look at our next equation, the y equation, and see what we can find from there. We're really just going through these one at a time, and we're not trying to make any assumptions about the fact that we actually know what the answers are. So I'm going to move the theta dot squared to the other side, and I'm going to pull the ys out. So we're going to get, and we put this to the other side, so that's going to be a plus. Right now, we see that ys is equal to 0 will satisfy this equation. But what about ys not equal to 0? Well, we know that this quantity is going to be negative, right? Because we know these are all positive. But then this quantity is positive. So we have a negative plus a positive. So actually, maybe there is an equilibrium point for ys not equal to 0. That's going to happen if we can find a value for gm1 over r13 cubed minus negative gm1 over r13 cubed minus g. So let's go ahead and start that. So case 1. What's that going to tell us? That's going to equal to g by, and so we can bring the g over to the other side and we get theta dot squared over g is equal to, so what do we achieve by doing this? Well, we can rewrite m1 over r13 cubed in terms of theta dot squared g and m2. So what we can do, now that we have something here, let's take a look at this other equation and plug things into there and see what we find. So here we have 6. Let's plug in theta dot squared actually. Instead of plugging in this one, we'll plug in the theta dot squared into here and we'll see what happens. Equals, so, okay. Let's try to split out all of the xs terms. So we have these two are going to cancel out, and then these are going to cancel out as well. And so what we're left is, we're going to move this one to the other side, and we're going to see that we have is equal to, so we can get rid of those. And this looks like a good opportunity to take advantage of the fact that we can write x1 and x2 in terms of the other, or at least we can write them both in terms of L. So remember from this page, we have these relations. So let's go ahead and plug those in. So we're going to end up with times x1, which is m2L, so that's going to be m2L over m1 plus m2. It's going to equal times x2, which is m1L over m1 plus m2. Notice that we can cancel out all of these. The denominator, it's m1, m2 times L, and the numerator here is m1 plus m2, so those all go away. And so what we're left with is, and of course we can flip these, which means that R13 is equal to the norm of R23. Okay. This is simplifying rather nicely. It feels like we're getting somewhere. So let's remember our definitions for R13 and R23. We actually never defined those, did we? So in this case, we got to note that the norm, not a lot of room to write here. We'll note that the norm of R13 is going to be equal to the square root of xs plus x1 squared plus ys squared plus zs squared. And then similarly, the norm for R23 is equal to pretty standard vector norm here. So we can now write these here. So we can say, okay, that's pretty sweet. We can square both sides and we can get, these are going to go away, these go away. And now we can take the square root of these, but you have to remember that when you take the square root of a quantity squared, the answer is actually the absolute value. So you end up with absolute value of xs plus x1 is equal to the absolute value of xs minus x2. So this algebra is simplifying really nicely. It's pretty great. So now we have these two absolute values. So there's essentially four cases where these could be equal, right? Like this one, the value xs plus x1 could be negative, while the value xs minus x2 could be positive, and then, you know, that's a case where these could be equal, or vice versa, or these values could both be positive, or they could both be negative. So let's consider those cases within a case, right? Because remember, this is the case of ys does not equal 0. So we still do have to get back to ys, but we'll get back to that in a second. We'll have xs minus x2 is less than 0, xs minus x2 is greater than 0, xs plus x1 is less than 0, and xs plus x1 is greater than 0. So let's think about these intuitively for a second. What does it mean for xs plus x1 to be less than 0 simultaneously with xs minus x2 being less than 0? Well, for xs plus x1 to be less than 0, that means that our spacecraft has to be on this side of the Earth, because this whole quantity is negative. Then for xs minus x2 to be 0, that just means that x2 has to be on this side of the moon. Well, the case where both of those are simultaneously true is when we're on this side of the Earth. Let's consider that. We're going to call this 1, 2, 3, 4. So case 1, we're going to have negative xs plus x1 equal to negative xs minus x2. So we can take the negative away, and we see that that's going to give us the xs's go away, and we see x1 is equal to minus x2. What? That doesn't make any sense. What I think this is essentially telling us is that for that case where the spacecraft is located on this side of the Earth, there is no solution to this equation, which, again, looking at the fact that we do know where the answers are when the case of ys is not equal to 0 is considered, the only two Lagrange points are the equilateral triangle points, which we know are in between the Earth and the Moon. So that's making sense so far. Again, we're trying not to cheat too much by knowing the answer, but we can kind of use it to help sanity check ourselves and make sure that we're going about the math the right way. So let's consider case 2. So for xs minus x2 to be positive, that means the spacecraft has to be on this side of the Moon. But for xs plus x1 to be negative, that means we have to be on this side of the Earth. So we can't simultaneously be in these two places. So this one we can just say does not exist. So now let's consider case 3. Here, we're on the left side of the Moon, but xs plus x1 is greater than 0, which means we're on this side of the Earth. So that seems plausible, right? We could definitely be there. So if we were to write out the math for this case, xs plus x1 is the quantity is greater than 0, so that one stays as is. And then because this one's less than 0, we put a minus sign in front of it. If you write that out, you bring the xs over to the other side and the x1 over to that side, and you get 2xs is equal to x2 minus x1. So you have xs is equal to x2 minus x1 over 2. So this is pretty close to what we determined the x-coordinate is going to be, but we said the x-coordinate is L over 2, and we also noted that L was equal to x1 plus x2, but here we have x1 minus x2. Well, what's going on there? Well, here we have to remember our coordinate system. So in here, as we drew this, the x is measured from the Earth to the Lagrange point. But in our coordinate system, we didn't center it at the Earth, we centered it at the barycenter. So if we want to transfer it to an Earth-centered coordinate system, we basically have to add x1 to our answer, and so that would give us x2 plus x1 over 2. That's equal to L over 2. Okay, so now for the sake of posterity, let's consider the case 4. And so that's when both are positive, so that means that the spacecraft is on this side of the Earth and the Moon. And so that's essentially the same as here, right? We basically have xs plus x1 is equal to xs minus x2. And then that's the same math for here, where we're going to get x1 is equal to negative x2. So that's just telling us that there's no solution to these equations in the case where ys is not equal to 0 and the spacecraft is on this side of the Moon. Okay, so we have xs, but we're still not done, and we need to go through and figure out the math for ys. Well, how are we going to figure out ys? We're going to go back to the equations that we wrote here, and we're going to do a bunch more algebra using what we know for xs, and eventually we'll be able to find ys. Okay, so now for finding the y-coordinate of the equilibrium point for which we just found the x-coordinate. So for that one, we're going to go back to this equation, and we're basically going to plug in the x-coordinate here, and we're going to find that these two denominators come up equal, and we're going to go from there. Let's get started. Page 7, we're still looking at the case ys does not equal 0, and we found that xs is equal to x2 minus x1 over 2. If we bring that into here, we're going to see let's take a look at this. So we know that zs is equal to 0. We can go ahead and plug in the equations for r13 and r23 and plug in our xs and zs, and we should be able to ultimately come up with something for ys plus, and this is cubed. From here, we can see that this is going to be L over 2, and then this one's going to be negative L over 2, but it's squared, so that's going to give you L squared over 4 for both of those cases is equal to, and don't forget, cubed. Square root cubed. Now we can add those two, so let's do a little bit of rearranging. We're going to want ys on top, not on the bottom, right? So we're going to move this square root over to the other side, and we're going to move the g over theta dot squared to the other side. The obvious next move is to take the cube root and then square both sides. Let's start with just the cube root, and then we'll square both sides. And actually, I'm not sure why I did those in two separate steps. I was trying to watch out for the plus minus that I know I'm gonna need to get with ys for my results to match what I expect them to match, but actually that's gonna happen when we take a square root in just a second here. But so let's square it first. Cubed and square rooted, so that's 3 halves. Sorry, wrong way. Squared and cube rooted. So ys squared is equal to, so that means that ys, now remember when you take a square root, it's going to be plus or minus the square root of, well, we could stop here. We have an equation for ys where we know all the variables, right? We know m1, we know m2, we know g, we know theta dot, and we know L. So this is fine. And honestly, if I was discovering this for the first time, I probably wouldn't go any further. I'd be like, oh, I got a nice equation. But we know from our trigonometry earlier that y is supposed to equal this nice square root of 3 over 2L. So how do we reconcile these two? Well, the trick is to look at the theta dot squared term and to take advantage of what we know about the two-body problem, which I haven't covered here, but, you know, it's a known thing. So we know that theta dot, because we're in a circular orbit, we know that theta dot is going to be equal to 2 pi divided by the period of the orbit. here I'm basically just using distance equals rate times time thing, right? We know that the radians per second that it covers is the total radians in one revolution, 2 pi, divided by the time it takes to complete that revolution, which I'm calling t. So then we know that the period, again we use distance equals rate times time, and time equals distance divided by rate, for the spacecraft to traverse that orbit. It has to go through the circumference of the orbit, which is 2 pi L, divided by the velocity. And from what we know about the two-body problem, we know that the velocity is equal to the square root of mu over L, where mu in this case is equal to g times m1 plus m2. If we plug t into here, theta dot is equal to, so that goes away. And then we can write this as times 1 over L. Basically pull a 1 over L squared into here, and you're going to get an L cubed. So that's going to equal square root of cubed. So now, here we have theta dot squared. So we can say theta dot squared is equal to cubed. See where I'm going with this yet? So now if we plug this back into here, we're going to see that ys is equal to m1 plus m2. That's going to go away, and this whole thing is to the 2/3. Well, hey, if you square something, if you cube something and then square it and then take the cube root, you're going to end up with L squared. Let's just add the last segment here. So then we can say this is equal to the square root. Obviously, we can pull an L squared out. And then what's left is going to be 1 minus 1 over 4. Well, that's 3 over 4. Square root of 3 over 4 is square root of 3 over 2. Plus or minus L times the square root of 3 over 2. So that's really cool. We started with, where'd they go? We started with these equations, and we've gone through 2 of the equations, and we've discovered that there are equilibrium points where x is equal to L over 2 and y is equal to plus or minus square root of 3 over 2 times L. But we still have one equation to look at, so let's examine that case. Or rather, we have another case to look at, which is the case for ys is equal to 0. Obviously, the only equation to investigate in that case is going to be this one. So let's go ahead and take a look at that one. Page 8, and so now we're looking at the case ys equals 0 and zs equals 0. So that means that we can say something right off the bat about R13 and R23. R13 is equal to the square root of xs plus x1 squared plus ys squared plus zs squared. But if these are 0, then we can say that this is going to be equal to the absolute value of xs plus x1. And then likewise, for R23, we're going to note that this is going to be equal to the absolute value of xs minus x2 for the same reason. So let's go ahead and plug these into this equation here and see what we find. Negative theta dot squared xs is equal to negative g m1 over the absolute value of xs plus x1 cubed times xs plus x1 minus. So now I'm just going to note that when you have the absolute value of something cubed, that's the same as saying that it's something squared times the absolute value, because of course when you square the term, it's going to be positive no matter what. So these are going to be equivalent. And I think it's probably pretty obvious that the reason I say this is because I want to pull an xs plus x1 squared out of here so that I can cancel it with this term, and likewise for here. And so this one's going to go away, this one's going to go away, and we're left with... From here, we're not going to be able to simplify the algebra any further. You can try if you want, but ultimately, at this point, we need to turn to some sort of numerical method to find it. Again, going with the theme of how would we do this if we were discovering it ourselves? Well, honestly, the first thing we might do is spend a lot of time trying to algebra our way out of this, and then give up, angry, go cool off, and then come back and think, okay, well, I have an equation that's equal to 0. I know how to find the roots of an equation. I know I'm going to need an initial guess first, right? Like I need to see, where could this thing be 0? I mean, for all I know, there is no 0 here, right? If I'm discovering this for the first time, I don't know. So I think my first step is going to be to plot it. And so we're going to head over to Python to do that. Okay, so we're going to do a little bit of Python to find the remaining equilibrium points. Specifically, we're going to go to the equation that we just found. We're going to type it up, we're going to plot it, we're going to take a look at where the roots might be, and then we're going to use some root finding tools to figure out what those roots exactly are. So let's get started.
So our equation has a bunch of constants. Specifically, it has the masses, the gravitational constant, as well as the distances from the origin of our coordinate system. So let's start with the gravitational constant. I'm going to say G equals, and now we're also going to use L equals 384,400. That's in kilometers. So since we have G in meters, let's go ahead and add 3 zeros to this to make it meters. So now we have x1 is equal to, and x2 is equal to m1 times L over those things. Okay, the last thing we need is theta dot. We know from doing our algebra that theta dot was equal to 2 pi divided by the period, and that the period was equal to the circumference divided by the velocity, and that the velocity was equal to, and the whole thing is going to be square rooted, which in Python that's the equivalent of exponent to the 1/2. So that's the velocity, which means that we have the period is equal to the circumference, for which we're going to need pi. So let's do some imports. Period is equal to 2 times pi times L divided by, and so now we have theta dot is equal to, so I guess we didn't have to import pi since it cancels out, but that's fine. Okay, so now we should be able to write our equation. So I'm going to write it as a function. So that's the first term, then we say minus G minus x2. And finally, okay, cool. So now I want to essentially solve this equation for a large variety of xs values and plot the result and see what I get. So to do that, we're going to import some stuff from NumPy. So let's do this. Xvals is equal to a range, and where should we take it from? Probably, there's sort of a question of like, if we were discovering this on our own, what would we guess for these values? I mean, I don't know. I'd probably look at the distance between the Earth and the Moon. Like, it probably wouldn't occur to me to look for L3, if I'm being honest. But since I happen to know that L3 is going to be there, I'm going to start this from, actually going to go from -2 times L, and we're going to go up to 2 times L. So basically twice the distance of the Earth to the Moon on one side of the Earth and to the other side of the Earth. And our step for that, let's do it in increments of a kilometer. So that should give us a fairly reasonable value. So then from here, we say yvals equals, and so now we should have something we can plot. Import matplotlib.pyplot as plt, and we're going to say plt.grid and plt.show. So let's take a look at what we got here. So remember that we're using this to try to find, we're examining this equation, we're going to figure out what sort of numbers we got to give to the root finder. Matplotlib.pylot. Okay, we got to do pyplot. So let's take a look at this. Okay, so it seems like for around the location of the Earth, we're getting an extremely large value. So we can try zooming in here, but I think what we probably ought to do instead, yeah, each time I zoom in, it's only going down by like 1 or 2 orders of magnitude, it seems. So probably what we should do is just fix the Y limit. So I think the way to do that is, let's see, let's go down to the bottom, plt.ylim, and let's just set it from -1 to 1, because we really only care about the 0 crossing. So let's see what that looks like. That's interesting. It looks like our equation is a bit incorrect. Let's do, take a look here. Okay, so now we're seeing the 0 crossings. There's one here, and only one here, and It's a little odd. Okay, after much troubleshooting, I have found that the issue was here, where we forgot to do E24 on this guy. So if we plot again, so this looks a bit busier, but it looks like we have some more zero crossings. We got one here, and one here, and it looks like there's two more. But actually what's going on here is that this is the position of the Earth and this is the position of the Moon, and our function is going up to infinity here and coming up from minus infinity here. So this line, and likewise over here, so this line is just an artifact of the plotting program. So we need to look at what these values are so that we have something for our root finding software. And so this one looks like it's about negative 3.92 e to the 8. This one's about 3.21 e to the 8. And this one's about 4.43 e to the 8. Getting here, and we'll put our root finding up here. So we're going to say from scipy dot optimize root scalar. And so now we're going to give it, let's see here. So we'll look for the various points. We're going to say L3 is equal to root scalar. We got to give it our equations, and then we have to give it a bracket. So we know that our one value was around negative 3.82 E8. So let's start with negative 4 E8, and then we'll go to negative 2 E8. That ought to be fine. And we'll have it print L3, and then we'll do something similar for the next two. And so let's take a look at what that's going to give us. So we print these things. Let's see. So we got one value at negative 386,000, and one value at 321,000, and one value at 444,000. Now, how does that compare to our what we wrote down? Well, what we wrote down happened to have been from Wikipedia, and so we're a little off, right? If I shrink this a little bit further so we can try to have both of these on screen at the same time, L1 should be 3.26, instead it's 3.21. L3 should be negative 3.81, 3.86. Well, again, we have to remember our coordinate system. So we're actually in a coordinate system centered around the center of mass of the Earth and the Moon, whereas these are written as distance from the Earth. So if we take our values, whoops, gotta find that plot, cancel it, there we go. If we print L3 plus X1, now if we, whoops, oh, that's right, I have to say dot root. Let's do that. Dot root. Okay, so let's not worry about this figure, and let's bring up Wikipedia again. So what do we got here? For L1, 326,300, and okay, this one's 39. Here we have 38. For L2, 4489. That's looking pretty good. And for L3, negative 3.8168, negative 3.8168. And so there we have it. So obviously Euler didn't use a computer when he was figuring out the collinear Lagrange points. He may have still used some kind of Newton's method. He found those Lagrange points, and we found them the same way. You know, it took us a little bit of Python coding, whereas maybe Euler had to go through a bunch of iterations. But essentially, we've solved this problem. And if we look back to the equations that we had on page 5, like, we've gone through all these equations now, and so we found, you know, we looked at z, and we saw that any equilibrium point has to have z equals 0. Then we looked at the second equation, and we found that there are two cases that satisfy that equation, y not equal to 0 and y equal to 0. So we looked at y not equal to 0, and we found the L4 and L5 points through a bunch of algebraic manipulations. Then we looked at the case for y is equal to 0, and then we did a bunch more algebra, and we used some root finding tools, and we found the collinear points. And then we checked our math. So that's it. Thanks for watching.